All right, thanks for coming, everybody. My name is Jesse Willett, and I realize that you have a choice of 3 or 4 talks today on using Redis for critical job queues. Thank you for coming to mine. I've enjoyed the last 2 that I've seen, and I hope you have too. I think that to be more accurate, I should probably title my presentation Reliable Priority Queues. So if you're here for durable over reliable, I apologize. The rest of it is all exactly what it says on the tin. For durability, we use the HA mode of Redis Labs Enterprise Cluster. It works great. So, okay. So ProsperWorks, introducing ourselves, is we're a multi-tenant CRM as a service, which, if you don't know, that's customer relations management software that's useful for organizing the process of sales teams or customer service teams. We were built with 3 basic principles in mind: keep it simple, show what matters, and make it actionable. So one of the ways we do that, this is a mock-up of our Gmail add-on, is that we provide all your customer information about your customer integrated with your Gmail experience whenever you're looking at an interaction with that customer. We do lots of other things as well. We help businesses sell more with a CRM that teams actually love to use. Okay, on to the more technical stuff. Well, on to me. I'm a server architect. I'm focused on storage, scaling, and asynchronous workloads. I worked at scale on public-facing live services on several different stacks. At ProsperWorks, we use Postgres with Citus, Redis, and Elasticsearch over Ruby on Rails. At Lyft, they use MongoDB and Redis using Doctrine as their ORM on PHP. And at Zynga, they used Memcache, Membase, and a lot of custom libraries over PHP. I've done image processing grids, phone games, text search engines, PC strategy games, desktop publishing, and every one of these systems had queues for managing work of some kind. And I've come to realize that queues are naturally managed the impedance mismatch between systems with different times or cost signatures. My team really liked that line, so I bolded it and I set it off. I've realized since that I should probably add, and the correct place to put your queue is in the lowest impedance component available. I'm presenting Ick, which is a Redis-based priority queue that we've used in our live Postgres to Elasticsearch pipeline since Q3 of 2015. We actually use it for several dozen other use cases. It's starting to grow, and we use it to replace, we use it as kind of a scalable cron. We do once every 4-day jobs for all of our users, once every 18-hour jobs for all of our users, once every 5 jobs for all of our active users. We do a variety of other pipelines with it, but mostly it drives, originally, Postgres to Elasticsearch pipeline. It's an extension of the Redis sorted set, to which we've added 175 lines of Redis Lua code. And we've found a combination that very neatly solves a lot of the problems that we face with asynchronous job processing. And Ick was my gut reaction the first time we talked about closing a race condition by putting some Redis into our Lua into our storage tier. But it was wildly successful for our needs, so we backronymed it as an indexing queue. It is available open source with the MIT license under a Ruby gem and bound to Ruby, but it would probably not be hard to extract it and use it from another dynamic framework. And so far, we are the only customer of that library, and I'm the only maintainer. So I'm hoping that some of you will get interested and at least challenge me on some of our assumptions and maybe get some good use out of it. I think it's fair to compare it to a lot of other solutions that are out there. There's the well-established Redis reliable queue pattern. That's documented on the Redis site. That's the use of r-push-lpop or br-push-lpop to move messages from one list to another list to indicate that they're being processed, but so that they're still retrievable if the processing fails. Ick is sort of the same idea applied to sorted sets, and we have some custom score management that drives it home. Redis streams, they don't support deduplication, which is a key use case for us, but we probably would have used them if they were around 3 years ago. I'm pretty excited about them. Apache Kafka doesn't really, log compaction might let us achieve some of our deduplication, but not very clearly how. It doesn't let us reorder messages. Other streaming services also don't let us reorder the way we like to. And our perception is that it was too costly to own or rent Kafka in 2015 for a team of 7 engineers. Now we could probably rent it. The cost to rent is much lower, but it's still yet another storage service. Ditto Amazon Kinesis. It probably was more cost-effective for our needs in 2015. It may not be more cost-effective today, but it's yet another storage stack, and we don't want to be having to worry about connecting another storage stack if we can help it. Our primary storage is Postgres. I'm just going to put that right out there. We have a heavily normalized entity relationship model that's common if you're a Rails application. Rails encourages that, and our dev team likes to build those. Elasticsearch hosts, for historical reasons, a denormalized form of our entities that we used in early days to give us scale, and we continue to use for advanced search. We're now happily on Citus Postgres, which solves scale for us very nicely. So Elasticsearch's use for scale is vestigial, but we still use the advanced search. So we have a mapping that we maintain from our normalized relationships in Postgres to the denormalized blobs in Elasticsearch. That's tightly coupled with our business logic, and we like having that be controlled by our code. That's one of the reasons why we haven't jumped on bottled water. Plus, nobody seems to be using it. The challenges keeping Elasticsearch up to date with live changes in Postgres are that we have high-frequency changes coming from our front end onto Postgres. Lots of small updates all the time, going all the time in a way that we try to make as scalable as possible. Also, we have asynchronous jobs making changes to the data that needs to be reflected quickly into Elasticsearch. But we can't, even though we have a really high storage and search bandwidth on Elasticsearch, we can't actually ingest as fast as we're making updates to Postgres. So we have low frequency of slow bulk API calls, and we need to match those together. And that tension is one of the impedance mismatches that I mentioned before. We accept a few seconds of latency in this pipeline. We're happy with that. But if we get to minutes of latencies or hour of latency, our user experience is degrading very badly and we're having a crisis. It's a really natural pattern. Probably a lot of you do it. When something gets written to your primary store or somewhere else, you also put the ID or some kind of a message in a Redis queue. In some cases, you might also dirty entries in Postgres directly or search for dirty entries in your primary store. We do. And then you have a background consumer process that's handling the copying. I hope that sounds familiar to a lot of you. It sure seems familiar to other folks that are presenting queuing solutions today. Okay, so we never implemented this, but I'll start at the beginning with the basic list pattern. We're just using, this is in Ruby. Some of our code does not map to an exact Redis operation, so I chose to present this in Ruby, but hopefully it's close enough to your favorite pseudocode for you to interpret it. The producer pushes a message to a key with rpush, and then consumer lpops a certain number of those, and now has a private batch that has those messages in it, is the only copy of those messages, which it then processes slowly. This is simple. This is more or less how Rescue works, and lots of other libraries that are just out there in the Ruby and the Redis space. Scaling to many workers is straightforward. You can have lots of workers popping off of the same list. But the disadvantages are that if you go down as a processor, as a consumer, you're the only copy of that message, and that message is lost to the system. Also, because it's a strict FIFO and there's no deduplication, if you start falling behind, you start falling behind really fast. And also, I didn't know it, but I learned in the last talk that LREM is O of N. So that's a drawback that I didn't realize because we skipped this implementation. We really care about deduplication in our space. We might have one piece of user data that gets updated a dozen times a second in an extreme case, or certainly a handful of times in a minute as a user does something really active, or unfortunately our model focuses dirtiness onto certain parts of the entity relationship model more than others. But we have entities that are dirtied several times a second. And under heavy load, our individual ES bulk APIs calls can take 5 seconds or more. So that's another impedance mismatch. And with too much hot data, our backlog can just keep running away from us and growing without bound, and then we have the problem of Redis filling up and other problems failing, other systems failing. So we get leverage over this problem. We want to deduplicate those messages. We don't want to have a message that is dirtied in Postgres 12 times in 5 seconds, get copied to Elasticsearch 12 times in 5 seconds. We only want to copy it once. So we prefer deduplication. We prefer deduplication at the queue level. We considered and rejected a lock per message at enqueue time to prevent us from enqueuing messages repeatedly. That's brittle and expensive. Those locks can leak if you crash, and they involve extra round trips per message to Redis. We considered version information in the message, which probably would have worked, like saying this entity got dirtied at this time, and when we have a large batch of messages, we only dedupe the most recent one. But we would have lost generality. The solution wouldn't have been applicable to some of the other cases that we've applied it to since then. So I think we're making good time. So naturally, we use sorted sets. Sorted sets for deduplication in Redis. This is straight from the docs. They are a data type which is similar in mix to set and a hash. Like sets, they're composed of unique non-repeating elements, strings. So that's our favorite property of it. And our second favorite property, of course, is that they're taken in order by score, which is a numeric value. Also, the log-n access time, or maybe it's m times log-n if you're accessing m things, I think, amortizes to log-n per item. And it's versus the O of 1 of lists, but I guess lists have an O of n on ZREM, so that's a drawback there. And they're deduplicated, so we get that property. But as long as we constrain ourselves to using scores that, like in Redis streams, are approximately a timestamp of the current time, we're almost Q-like, we're almost FIFO-like. And that's important for managing SLAs, but we're not always FIFO-like. So then we moved to this. This was actually live. We had this live for a while. This is the basic sorted set pattern, where we go to Redis every time we have a message. We use the sorted set add operator using the current time stamp as a score and our message as before. And then the consumer can get a range. It can get all the lowest scored items from the queue in a batch. It can fetch batch-sized things in one operation, which is good for amortizing Redis ops. It processes them slowly, and then only when it's successful, it removes those particular messages back from Redis. So if we have a failure doing process batch slowly, there's another copy still waiting in Redis of that message for us to consume on a subsequent pass. We get the deduplication for free from the sorted sets, and because we have a nice, clean, batch-oriented Z range by rank, we have 1 plus 2 over batch size Redis ops per message, down from 2 Redis ops per message. And we are sometimes constrained on Redis ops. That is sometimes our bottleneck when things get really hot. So we watch that closely. Actually, packets per second, but our best proxy is ops. We also pipeline heavily. Disadvantages are that there's a big old obvious race condition between Z range by rank and ZREM, which is that if we're processing a message and it's in the current batch and it gets dirtied again, it's now been added with another timestamp. And probably the thing that we're writing to Elasticsearch is the thing from before it got most recently dirtied in ProsperWorks. So when we go to the last line and we remove it from the data structure, we're now removing an indication of an update in Postgres which hasn't gotten to Elasticsearch yet. For really hot data, we might miss one dirty and not propagate it. So that was, it didn't take long before we found that. I actually hadn't joined yet. Actually, the next solution also I didn't contribute to. But here was a big improvement that the team made. They made an improvement constraining the size of that critical section. It added another round trip, or actually quite a bit of expense per message. But it replaced that simple, I'm just going to do a little animation trick, that ZREM expanded to 3 lines at the bottom, where we repeat fetching the batch. We identify only the things that are common in both batches, so we rule out things that might have changed between before and after process batch slowly, and then we remove only the things that are unchanged. So we still have a critical section, but that critical section is only within the last 3 lines, which is probably an order of magnitude or more faster than the wrapping process batch slowly. And I think I have already stated all the advantages and disadvantages. Okay. We really care about hot data, though. I mentioned it before, and now I have a whole slide for it. The storage set solution has this critical section where we lose the dirty signals, and it's got a more subtle problem with hot data. We can imagine something that's being added with a higher score continually, much faster than batches over an extended period of time. So when we get to an immediate load, we could have a steady state of maybe 1,000 or 10,000 items in our queue. And every time we go to pop 100 or 1,000 of those items to write them to Elasticsearch, the really hot data has been pulled out of the low end and pushed into the top end. And if it's really hot data and it changes faster than every 5 seconds, it might always be out there at the end of the list of 10,000 items, and we're only popping from the bottom 100 or 1,000. And hours can go by when that condition obtains that that message is still being pulled beyond the wavefront that we're updating in Elasticsearch. So this was when we realized that we had this problem, that kind of like tipped the balance, and we decided we needed to do some real data structure work. And we gave this a name, and I still present it here, and I present it internally, the hot data starvation problem. It was subtle, we didn't anticipate it, but it was real, and when we measured it, it was costing us a lot of important updates. So, we wrote Ick. It is a pair of Redis sorted sets. There's a producer set and a consumer set. And most of the benefits I already mentioned the original solution still obtain, and it's by benefit of using the same basic data structure. But in Lua, and with help from some Ruby bindings, we implement 3 main operations now. There's ICKAdd that adds messages to the producer set, exactly like ZAdd does. And then ICKRESERVE is the most subtle operation. It identifies the lowest scored messages in the in the producer set. I used both. It takes them out of the producer set, copies them into another set, the consumer set, which is only updated by the consumer. And then it returns the contents of the consumer set to the processor. Later, ICKCommit comes along and just removes messages from the consumer set. Both of these operations, ICKAdd, when we're adding things to the producer set, and ICKRESERVE, when we're moving things into the consumer set, whenever they encounter a collision, like the value is already in the sorted set, they select the minimum score. So the data is, and then this is about as fancy as I get with diagrams, which work well in different presentation media, but aren't that fancy. The data flow is ICKAdd puts a bunch of messages into the P set, ICKRESERVE effectively gets end messages for you, but they're still available and they'll still be there the next time you call reserve, and commit tells the producer set to forget about them. The add operation, it's variadic. It'll take multiple messages. It results in a producer set that is a sorted set on the scores, as shown. If you add another value with a higher score, nothing changes. If you had a duplicate, but the score is higher, the value stays the original value. But if you had a duplicate with a lower score, it moves down to the lower score and it changes the ordering relative to other elements. This is very similar to ZAddXX, which does not update a score if an item is already present. And I could probably substitute this comparison logic with ZAddXX and lose very little fidelity, but that operation only became live in Redis 3.02, and in 2015 we were on 2.8 or 2.6 or something, so we didn't have it. And it's not quite the same. Ours is more predictable, it's definite, and assuming the new scores trend up over time, and then there is no starvation here. The hot data starvation problem is gone. Old scores never go up, so all the messages that are already in the data set, no matter what new dirtiness arrives for them, trend down to the lowest end where they get popped. ICKRESERVE, I'm going to expand on it now. I can add 3 messages with an ICKAdd, and then I reserve 2 of them, which leaves the highest score one in the producer set for later, moves the lowest 2 into the consumer set, and returns those lowest 2 in the same format as zrange back to the application. Looks like I have a wrapping problem there, but I haven't lost a line, so that's okay. ICKRESERVE could be called again, and it would have no net effects if it were called again without anything else in there. It would notice that the C set was already full up to size 2, and it would just return that again. So that's your recovery mode. The merge operation, if there happened to be something that were in both the C set and the P set, also respects the minimum score rule. And then ICKCommit is the simplest one in concept. If you've already got something that's been added and then it's been reserved, ICKCommit purges that thing from the C set. And that's how the system is able to positively acknowledge message success and drain the message from the system. Okay. All the ICK operations are bulk operations. I profoundly believe that your bulk API should always be your first API. There's a lot of reasons to want to amortize connections and round trips and do trade-offs between different parts of the time, space, bulk product. So everything should be a bulk operation, even if you only use it as a singleton. Duplicate messages are always resolved to the minimum score, as I mentioned. Current timestamps are used in most cases for the scores. Even hot data doesn't get bumped in front of. Nothing gets cut in front of in line. Hot data never gets relegated out to the far end of the queue. And a message can be in both the P set and the C set. That'll be deduped when you fold another reserve statement. But this is a good thing. On the face of it, it feels like if I've got a message that's ended up both in the current batch and in some future batch, I'm now on track to do multiple updates to Elasticsearch or multiple expensive downstream operations on that data. But actually, it exactly reifies the critical section where, from the point of view of the data structure, it is indeterminate what state the downstream system is in. When this system is reading that it's working on something right now and there's something in the C set, we don't know whether we're looking at the underlying Postgres and seeing the old data or the intermediate data or the future data. So the fact that it's going to come up again in another batch actually captures our need to rewrite it only after each update. So here's the same solutions as before, but in the Ick pattern. Ick.new Redis, I know does not make sense outside of the context of this. I would have preferred to have been able to say, this is a Redis command, this is how you call Ick in Redis, but it's Lua. So Ick.new.redis actually masks a whole lot of doing script load and eval SHA and testing if the thing is already there and handling return results differently if we're in a pipeline or not in a pipeline. So I've left it there and I'm just going to wave my hands over it. But basically the operation is ICK_add, which is a key and again a message, but there could be multiple messages there. And then reserve is much like we used a zrev range before, except we just ask for batch size, process them slowly, and we commit when we're done. And all the advantages and disadvantages here, except for scalability, I've already said. Critical section is completely hidden away in the atomicity that's guaranteed for a single Redis operation. Those 3 lines that I was worried about in the third solution, where we might lose a dirtiness signal, it's not possible because we're actually going to block taking the dirtiness signal into Redis while we're doing the reserve operation. But it's fast. It's way fast compared to what we do in Ruby or in Elasticsearch or in Postgres, so that's not an issue, usually. Hot data starvation is solved. Messages are only dropped from Redis after positive success. Disadvantages are you have to be willing and able to deploy Lua to your Redis, and it's not inherently scalable, which I have a whole slide to talk about, but I'm acknowledging it here. All right, so dealing with scale. Ick does not support scale directly. It's, I considered different patterns where I might allow this solution to scale up the way Redis streams or Kafka are going to scale up, and I rejected them because of scope and complexity, and there were questions that I didn't want to answer in Redis at the time. One of them is that a consumer process would need to identify itself so we could distinguish between what it was working on and what another consumer was working on. How are messages allocated to those consumers? How do consumers come and go? What happens if they evaporate or they're lost? They never come back, or there's more of them tomorrow than there were today? And what kind of serialization or deduplication guarantees are compromised by moving messages in process into different consumer sets or different space in the data structure to be processed by different consumers? And for our use case, actually, how could the app customize it? Some of our uses of Ick today shard. Well, our solution is we shard at the app by hashing the messages, and each Ick has a single consumer and only a single consumer. When we need more consumers on one workflow, we add shards, and the system rebalances messages. It says, oh, this message is in the wrong place. It goes to the right place, and we can add capacity that way. We decrease capacity that way at the application level. But we do suffer from head-of-line blocking, so we have to watch out for really slow jobs. But the advantage is, by pulling that back into the application, some of our use cases are not simple hashes over the string contents. In some cases, we hash by customer ID, or we hash by data type, or we hash by time slot. So these consumers tend to have work that has high locality of reference, and we can get a lot of leverage out of that, especially in our other sharded data stores. But it means that Ick is not a complete solution. Ick is not by itself the thing that you're going to scale to 100,000 workers on. You need some orchestration up above it. Actually, I'm about to enter some appendix slides. I've got like 3 wrap-up slides about future directions and things we do with it now. So would anybody like to answer questions about the basic material? I mean, ask. Yes, sir.
You mentioned a lot of Lua scripts. Do you have is there a Redis module that's tied
You mean?
together with this?
Okay, you ask about the Lua scripts and are we using a Redis module? The answer is no, we don't use a Redis module. I'm not sure when it was introduced, but certainly by 2.8, Lua support is built-in functionality of stock Redis. I think there's a strong argument that Redis module might be a natural place to implement Icks in a more readily consumable form, but at least in the last several quarters, that's been outside of my wheelhouse. I'd love to do it, but I don't think I'm actually going to do it. But I could consult on doing it. Yeah, so no modules at this time, and Lua is stock. There are complexities about moving Lua back and forth and combining that with pipelines if you're really looking at throughput and performance and round trip management. That there's a gem for how we solve it that's also out there, but you could use the Lua without that gem. Other questions on the core material? I should be clear about my enthusiasm about this data structure. It really solved a lot of problems that were really tanking us all the time. It's just that scalability is next to it, not on it. That's all right. I'll go ahead with the next couple of things. They actually illustrate part of why I'm excited about the data structure. Hilbert's SLA. We usually use the current time for the score in our icks, I mentioned, and that gives us a nice FIFO-like property. Any backlog that's already in the data structure has priority over current demand, and any future demand has less priority than current demand. And that's mostly what you want most of the time, especially for a bunch of users touching something from the front end that have equal importance. But unfortunately, resources are finite, and we alert when scores of the current batch get older. We're able to use that score as a sort of the date. How old is the message? Are we out of SLA? What's the latency been of the message? You could also do this with Redis streams, or just by putting the score in your Redis list queue. The date. But also, unfortunately, demand is bursty. Sometimes we have bulk imports or other bulk operations that our users do. We let them do bulk edits. We have bulk APIs that let them bring in lots of changes. We have an upload for CSV files or spreadsheets that could contain hundreds of thousands of rows that we try to ingest as fast as we can for the user. So those operations can produce huge volumes of things that need to be updated into Elasticsearch. So what we do is when we're doing a bulk operation, we offset the scores. We increase the scores so that the SLA on the bulk operations is lower priority than the SLA on stuff coming from the web. And the larger the bulk operation, the larger the offset. So if you've given me 100,000 rows, your last few rows aren't going to be out of SLA at my end for 20 minutes. And so basically in Unix terms, bulk operations get bulkier and nicer at the same time, which is a nice form of production leveling. This is something I just added recently on the train. It was really exciting. I was going on the train for vacation. It's a combination of the Ick commit and Ick operations into a single Redis round trip. To reduce the need to have two Redis round trips in order to benefit from a two-phase commit. This is a larger look at the larger structure of one of our consumers in the abstract. Before we were just looking at the inner loop, but now I've unpacked it a little bit. While we're still running that consumer, we go ahead and we get the next batch, but we also, and then we process that, and then the next batch becomes the last batch, and then we go back to the top of the loop, and we commit the messages from the last batch in the same round trip that we reserve the next batch size of messages for the next batch. So that cuts one of the round trips out in the process. And I actually think this pattern could be useful any place that you got two-phase commit or a pipelining processing system of any kind. That you could save like some downtime for components on both sides by dropping off the question for the future while picking up the results for the past, instead of making those two separate calls. Might offend your sense of modularity, logical modularity, but it appeals to my sense of conserving physical resources. And then this is another thing that I added that has the distasteful name of Backwash. This is in anticipation of using these icks as a scheduling mechanism to replace actually Rescue Scheduler, which for all future timestamps that you might schedule something in, for every second that you might schedule something for, it puts a list of the messages that you want to run in that second into Redis, which is great for keeping those small, but it's not great for keeping them visible. And unfortunately, we have some that are years out into the future because of some bugs in the past, and it's really hard to crawl all those and figure out what they are. So I'm looking to use icks as a scheduling mechanism, to schedule things very far into the future, and then have a new kind of consumer that doesn't consume them until we've reached the current time that matches their timestamp. But to do that, I wanted to make sure that I didn't have head-of-line blocking on messages in the far future. I have these examples that try to outline it, but I think I'll just free verbalize it. Suppose that I've got a queue that's full of 10,000 things that are meant to happen in an hour, and I've done a reservation of a batch of 100 of those and discovered that there's nothing to be done for an hour. So now the reserve set, the producer set, is locked in full of things that are an hour old. If something then gets scheduled that's due in a minute, it's going to be an hour before I find out about it, because I'm going to just keep coming back and looking at that reserved set and finding that everything's an hour old, and that poor thing is going to be stuck, starving off in the producer set, waiting until the consumer set is flushed. So Backwash basically flushes the consumer set back into the producer set, makes sure there's only one copy of every message in the entire system, and then brings the minimum score things back into the producer set. So you don't have stability necessarily between one reservation and the next reservation, but you do know that you're always looking at strictly the lowest score things in the total system, and you're not wedged behind something else. Ta-da. That's it. That's it. Thank you very much. And I spoke a little fast. I apologize for that. But we have 15 minutes to ask questions, so be generous with picking it apart. All right, then. Oh, wait. Yeah.
Do you have any names lined up for future products you might add to this in the same vein?
Oh, you like? I do like naming things. No. Backwash. Ick Exchange is probably. What are some names that we've used that are off color that aren't open? But Gremlins. We talk about Gremlins, which is where I'm looking at all of our asynchronous processing. We have different kinds of work going through Rescue or going through Ick-based systems. By the way, we're migrating all of our use of Rescue over to this, but it's a project that's quarters out before I can share it. I think I don't get to work 10 hours a day, So a gremlin is when we see a system that's got a lot of asynchronous processing over a particular domain of cost profiles for the jobs. All the jobs have 10% DB load and 30% RAM, or like the ratio of DB to RAM to CPU to network is in a particular stable domain. And like if we're all caught up and we're at steady state, then everything's fine. But we could have one job that suddenly starts behaving differently. It starts taking a lot more time, or it starts hitting the database a lot harder than it normally does. We call those gremlins because we used to not be able to see them. We built monitoring to be able to see not just like what jobs have been popped and which jobs have been pushed, but actually in real time we've got a graph of how many workers are working on each job type. And the gremlin pops up really visibly as like it was cruising along only using 10 workers, and now it's using 100 workers, and the reason all our queues are backing up, this was the thing that was a gotcha for us. All of the queues that were backing up were always the high throughput queues, but it wasn't necessarily the high throughput jobs that had gone gremlin and were occupying all the workers. So simply analyzing push and pop rates wasn't easy for us to intuit. Like you could do a crazy integration that's not easy to do in Graphite, but I don't know. That's a name that I had, gremlins. It's a job that suddenly starts costing a very different amount than it did before, and it throws all your tuning out of whack. The right thing to do is slow down and back off on it and jail it. We have jails and chalets for jobs. Yeah. That's a really open-ended question, and I'm just filling time coming up with clever names. They're not that clever. Is there anything else? Yes, sir.
It took me a while to follow where you were going with your example, but I translated that as you're trying to introduce some means of suggesting a quality of service metric that's needed for each individual metric or each message.
Did I not leave any of those words in the presentation? I may not have. We switched from. Initially, we just thought of the timestamp as the time that the message was created. It was the time of origin, and we measured how old the message was. But when we switched to that concept of Hilbert's SLA, which is a joke name for you, Hilbert's Grand Hotel is a mathematical construct for understanding some of the difficulties of analyzing infinite sets. That involves having infinitely many spaces in time and moving all the guests, like maybe you have room 1, 2, 3, 4, 5 for as many as there are integers. You need to add infinitely many guests to your hotel, so you ask every guest to move up to n times 2. Now there's still infinitely many guests in there, but you have infinitely free rooms to put your next set of guests in. So Hilbert's SLA was, yes, an SLO management trick, service level objective, in that we switched from thinking about the timestamp as the time that the message was originated, and we switched to treating it as the time that it's due by. And if we're processing it after its due date, now we're out of SLO. And maybe SLA, but we haven't gotten any sophisticated contracts like that.
So when you talk about deduplicating, if you had 5 messages for the same key,
yeah,
they all have different timestamps on them. The other part that I was missing was that the message content, the value of each message, could be thrown away, it sounded like, when you were deduplicating. It didn't sound like you needed to merge values or do any...
Thank you for asking that. The question is, it sounded like I didn't need to do any merging of values. It sounded like messages could be thrown away. The content of the message could be thrown away when the deduplication happens. By virtue of using a Redis sorted set, the deduplication is on exactly the content of the message as a string. String identity is the deduplication function. So if I have messages A, B, C, D, E, F, G, A, the A is going to fold in with the first A. They're not deduplicated on timestamp or time. They're duplicated on content. If I want to use one of these in a context where I don't want to deduplicate messages, I'm going to have to put some random salt into each message.
Yeah, because I can see a real use case for deduplicating. Maybe that's not the right word that I'm thinking of. If I've got 5 messages, I can't lose any of the content, but I want to consolidate so I only send one downstream without losing fidelity.
But they are different.
They are different, but maybe they're complementary and they can be aggregated together.
I mean, that's
Depends
kind
on
of
your use
happening.
case,
Yeah,
yeah.
that's kind of happening here on our larger system. I mean, I take 5 messages or 100 messages and I send them to Elasticsearch in one round trip. Like there is a consolidation in the sense that I get an economy of scale but I make one call downstream from this. And I also put 5 messages into this at a time, and I pop 5 messages out of this at a time, and I commit 5 messages at a time. But if there are 5 messages that have different content in the queue itself, the queue will not deduplicate those. It will preserve their unique identity of every one of them. It'll only deduplicate messages that have identical string content. So,
Thank you.
yeah, my pleasure. Plenty of time. Yes, in the back, please. Retry. Well, this data structure supports retry. Let me try and get a good picture of it. Retry is supported in the data structure by this property, that if I do a reserve and then do another reserve immediately after that, or if you imagine I did a reserve, I start processing something and then I got killed off, my container got wiped out or there was an asteroid, you know, then when I come back and I do another reserve on the same data structure, I will get the same messages. The messages remain in the system until commit, and they will be returned on all subsequent reservations when you're looking for new work on that key until you've actually said that you're done. So then, let's see. This last line, if I crash 5 times in a row in process batch slowly, I'm going to see the same batch every time I resume. It's only after I'm successful and then I come down and tell Redis actively that I was happy with these messages, will they not keep coming through in future batches. Thank you.
Do you operationally make sure you have only one consumer running them?
For each one of these? Yes, I use a Redis lock, actually. I have a scheduler that actually looks at a bunch of environment variables and configuration that says what all the icks are, how many of them are there for each shard, for each purpose. That system is called batchers and crawlers. Maybe you can look for that in Q4. It's batchers and crawlers because it manages not only batches of work, but it's going to be heavily Ruby-based. It's not going to be maybe as applicable as this. It manages sort of clusters or bundles of these icks, but also it knows how to schedule the unique consumer for each one. And it does use Redis locks. But each consumer has like sort of a long life, like 5-10 seconds. So it'll come online, it'll say, I'm handling the Elasticsearch pipeline to this Elasticsearch instance. There's another Elasticsearch pipeline to another Elasticsearch instance, but I'm handling the 5th out of 15 shards for this Elasticsearch instance. I acquired the lock for that. So that lock is going to have a timeout of 5 minutes. I'm going to run for 4 minutes and then I'm going to quit. And while I'm running for 4 minutes, I'm going to loop on reserving and processing and reserving and processing. And then when I get to the end of that, I'm going to release my lock, I'm going to quit. And that gives my Ruby thread the possibility of doing any other work for any other batcher or any other ick. But it also releases the lock that lets any other thread pick up work on that particular queue if it's got backlog. But it also lets me, if the queue is empty, if there's not a lot going on in the queue, it lets me release that Ruby process back for other use. But yeah, I use Redis locks to make sure there are not 2 consumers on any one queue. And I have another management layer that I thought was that scope, but it's a good question, that makes sure that there are as a high frequency of workers looking at each queue. And that is coordinated with the other systems that know which queues it's legitimate to push messages in different cases. Any other questions? We're actually using the time well now. We're down to 5 minutes. All right. Thanks,
Thank you.
folks.